1 of x1. Boson, fermion wave function. Now let's take a case, as I said, where both wave functions are the same. Well, this just gives me twice the original wave function. All right, it may not be normalized correctly. We may have to normalize it appropriately, but it gives us twice the original wave function, and it's not zero. Nothing wrong with it. Again, it's two bosons in the same state. Perfectly good. But the fermionic construction here gives us what? Zero. So again, we can't make a state in which two fermions are in the same state. The same rule continues if you have multi-particle states. If you have multi-particle states, any number of particles, then the wave function is a function of many variables. And it has the property that for bosons, if you take any two of them and switch them, the wave function does not change sign. For fermions, if you take any two of them and switch them, it does change sign. Again, what happens if you switch twice so that you come back to the same configuration? Clearly, in both cases, nothing happens. Right. So the process of double swap is nothing at all. It's trivial. It doesn't do anything, as you would expect. As you would expect. But the odd thing is that the process of single swap, which you might have thought does nothing, changes the sign of the wave function for fermions. Okay, so that's, if you like, the basis, the mathematical basis, the mathematical set of rules that goes with the Pauli exclusion principle. You can't put two particles in the same state for fermions. Now, what about when the spin? Well, when the spin, the easiest way to think about it is just to add another, for each particle, instead of saying the wave function is only a function of position, think of it as a function of position and spin. So in that way, you can think of the wave function as a function of position, and let's say whether it's up or down. We could choose sigma z here. Z component of spin. This wave function has the following meaning. Its magnitude, its squared magnitude, is the probability to find a particle at position x with spin either up or down, depending on whether you put in sigma z as 1 or sigma z as minus. So it's a function of a continuous variable and a discrete variable plus or minus 1. And it represents the amplitude, the probability amplitude for the particle to have a certain rotation with a spin either up or down. Once you know that, then you say, okay, the wave function for many particles one here stands for the particle, not whether it's x, y, or z. That's 2, so forth and so on. This representing the wave function for a particle to be at position 1 with spin sigma 1, position 2 with spin sigma 2, and so forth and so on. And now the rule is exactly the same, that if you take all of the stuff that's associated with particle 1, that's both x and sigma, and you take the things which are associated with particle 2 and switch them, bosons, nothing happens, the fermion's spin change. The sign changes. All right, but what it boils down to is exactly what we said in the first place. You simply can't put two particles into the same state, including spin. Including the spin, if they're fermions, you can if they're bosons. Okay, any questions about that so far? Yeah.
You know what this sort of reminds me of a little bit is that you've got a bunch of things and you kind of interchange them for fermions, then you get a minus sign. So this makes me think about the permutation, the permutation.
These are the representations of permutation groups.
So that comes into this.
Yeah. Yeah. Switching the particles is a permutation, and what happens to them in the permutation, a plus or minus sign, defines a representation of the permutation group. Right. That's a very definite thing that has to do with permutations. So it not only reminds you of it, it is it.
Particle 2 and side 1. You wrote that as the product. Why not the sum?
Oh no, the sum of two wave functions is a wave function for one particle. It's simply the superposition of to build a theory of two particles. The state vectors are the tensor products, are in a tensor product space of the wave functions that depend on two variables. And no, you wouldn't want to add them. Adding them would correspond to putting a single particle into a superposition of states. So right, there's two things you can do if you have two wave functions. You can take a single particle and put it in the sum of the two of them, or you can take two particles and put one in one and one in the other, and for one in one and one in the other, remove the problem together. Is what? Well, so far I haven't. It certainly does give interference effects, but we haven't talked about interference yet. I may talk a little bit about interference later and the effects of these things. Indeed. That's right. You could say the Pauli exclusion. All right, fine. You could say the Pauli exclusion principle is a manifestation of a funny kind of interference where when you put the two particles in the same state and switch them, they interfere. Good. So yes, so it is a kind of interference phenomenon. You're right. Yeah. Yes. Yeah. Because when Pauli was doing it, he wasn't deriving the principle. It was an empirical fact. And he was, if you like, interpreting the principle, finding a mathematical framework in which the principle would be correct. Later on, of course, once there was a relativistic theory of particles, and this rule here became part of the logic, inescapable logic, then there was a derivation of the equivalence principle, not the exclusion principle. He was trying at first to describe an empirical fact. Of course, once he realized this, that there was such a nice mathematics to it, undoubtedly he started looking for deeper reasons for the mathematics, and eventually he found them. Dirac and Einstein were the people who really built this, and Bose, and Fermi, I suppose. I don't know, Phil,